So our speaker today is Maxime. He's a Ph.D. candidate, and this is the open portion of his university oral examination. A bit about him. He got his diploma in engineering, which is supposedly equivalent to a master's degree here from the École Centrale in Paris in 2013, and joined Stanford as a graduate student at that time. His undergraduate degree was the emphasis on management science. So when he came over to CTR and wanted to study fluid mechanics and turbulence, so we decided that he should be given a trial period. So he joined, he became actually a teaching assistant for 2 or 3 quarters. And at that time, I'll say a little bit more about his.
Hey, V, should I connect my laptop? Yeah.
These were undergraduate and graduate mathematics, computational mathematics courses, and they led to his getting one of the centennial TA awards here at Stanford. But what was unique about him was a lot of good teaching innovations in terms of helping designing the problem sets and putting instructive pieces on the web, online, for review of the subject matter, etc. So he was just outstanding there. On the research frontier, he has already published 6 journal papers in the physics of fluids, physical review fluids, and journal of fluid mechanics. And another article, the 7th one, I think, is pending in the International Journal of Multi-Phase Fluids. Another interesting aspect of Maxime's stay at Stanford was that he also showed considerable talent that came up in competitions of the gallery of fluid motion at the APS, the American Physical Society meetings. So last year he won with his colleagues won the Van Dyke Prize for the best poster, I guess, right? That was it. And in this poster, again, the technical content was quite nice. It was the first time I really had seen a visual picture, not a sketch, but a visual picture of the cascade process in a turbulent flow. That he did it with his wavelet analysis. And as an encore, this year in November, he also with his colleagues won a poster prize. And this one was quite interesting. His contribution to machine learning had to do with this, where he actually they wrote, the poster's title was Album of Fluid Motion 2, which is, as you know, Album of Fluid Motion was the Van Dyke's book, and depicts a lot of beautiful pictures in fluid mechanics, inspired these. So they decided that they are going to use machine learning and studying famous paintings of the old masters, Van Gogh, Picasso, and others, and try to replicate some of those photographs that are black and white in Van Dyke's book, and see as though those masters had painted them. How would they study the brush strokes and so forth. So I don't know what he's going to do next, but that's the one area he could choose a career. So without further ado, I'll let Maxime, but before, let me introduce the members of the reading committee here. Dr. Javier Urze, Professor Tajib Lele, Professor
Thank you very much, Professor Moyne, for this kind introduction, and welcome everyone. Thank you for attending my defense. It's a great pleasure for me to be sharing some of the work I've done during my PhD with you regarding particularly the exercise of Subgrid-Scale modeling and wavelet analysis to inform the former for inertial point particles in turbulence. And before I dive into the say technical part in this talk, let me maybe motivate this topic by reminding everybody that there are a lot of environmental and engineering flows that involves the coupling of turbulence and a dispersed phase. So here, for example, you can see volcanic ash after volcanic eruption, where quantities of interest in this context involve the dispersion of this volcanic ash for visibility for airplane traffic, but also for safety of the engines. Another example found in nature in the field of atmospheric physics, where the interplay of turbulence and cloud droplets in clouds both have an effect on the formation of rain, but also on the radiation properties of cloud and how the radiation, say, coming from the sun is transmitted through the clouds and the subsequent impact on climate. Another example is related to sandstorms, which can have quite devastating impact on urban environments. So this is an example on Earth, but you have similar examples in space. So this is a picture from the movie The Martian, where you see that basically this is the onset and dispersion of a dust storm. And it's worth mentioning here that the physical mechanism that explains the generation of this type of processes is not necessarily well understood, despite the consequences that it can have for the crew or for the equipment that is sent there. And as a last example, let me move to an engineering example related to the main project I've worked on in my PhD, which is related to particle-based solar receivers. So here is a picture taken in Nevada, where you can see an heliostat field made of thousands of mirrors that have a particular goal of focusing the light of the sun into a tower, which you might be able to discern on this picture. And the purpose of having this kind of engineering system can be varied, but the particular one that I have worked on during my PhD as part of the PSAP-2 program is related to the investigation of possible efficiency gains in particle-based solar receivers. So here is a sketch just to illustrate the complexity of the problem, and next I'm going to explain in what part of this problem I've particularly focused on. So basically the idea is that we have a cold turbulent inflow which is flowing down a duct, and this turbulent inflow is going to be subject to solar radiation. And since the flow is transparent and the objective is to heat it up, what we do is that we load the flow with solid particles that are opaque to the input radiation, and then hope that the radiation absorbed by the suspended particles, which is then released to the flow, is going to allow it to heat up the fluid and get a temperature profile at the outflow, which is higher than at the inflow. And lots of the questions here when it comes to engineering design are what kind of flow should we have, what kind of particles. So lots of physical parameters which are not well known to optimize the output profile. So this is a complex multi-physics phenomenon, and there is one particular physical process that happens in this flow, which is that of preferential concentration, which is a term that means that when particles, inertial particles, are suspended in a turbulent flow, they tend to sample the flow in a biased way. And because of that biased sampling, this produces non-uniform spatial distribution of particles. And those non-uniform spatial distribution of particles have a critical effect on the subsequent prediction of the macroscopic quantity of interest. Because, for example, for this case, you can imagine that since the particles are the medium through which the flow is heated, the exact location of where those particles are, whether they are clustered or not, is going to have a direct impact on how the flow itself is heated. So this is the quantity of interest that I'm going to talk about in this talk, is how can we predict in numerical simulation this phenomenon of preferential concentration. And in the PSAP Center, the reference methodology that we are using to compute this phenomenon is one that we call point-particle DNS. So the idea is that we are solving the incompressible Navier-Stokes equation for the flow on a Eulerian grid by solving all the flow length scale down to the Kolmogorov. And because we have very small particles in the experiments that are much heavier than the fluid and which lead to, in general, low particle Reynolds number, we can have a simple representation of the equation of motion that is solved for every single particle. So particles are treated as points. We do not resolve the scales around each particles, and we just solve these two ODEs for individual particles. And furthermore, in this talk, to isolate the effect that I'm going to describe in a moment, we are going to be considering a dilute suspension of particle, meaning that the number of particles is not going to be that large enough for the dispersed phase to have a feedback force on the Navier-Stokes equation. So we have a one-way coupled scenario here. And I want to draw your attention to a particular dimensionless number that arises in this physical regime, which I'm considering here, which is a Stokes number, which is a ratio of the particle characteristic timescale to a flow timescales. And in what I'm going to show next, maybe the most relevant one is the one defined based on the smallest flow timescale, which we call the Kolmogorov timescale here. And the main idea behind this parameter, to give you an intuitive feeling for what it represents, is that you can think of low value of the Stokes number as being representative of dust-like particles that are going to basically follow the flow, going to be tracers, and large Stokes number as being characteristic of larger stone-like particles that are going to be inertial to the small fluctuations, that are not energetic enough to move them around, but that are maybe going to trace the larger ones. So this is a reference methodology that we use in the center, and it yields reasonable agreements when it comes to predicting the preferential concentration of particles. However, the cost associated with resolving all the flow length scales becomes prohibitive when one is interested in simulating real-world applications. So the numerical modeling approach which I am interested in is the one that we call point particle LES framework, in which instead of solving for the full scale velocity u, instead we are going to solve for the large scale velocity u bar, which is formally defined as a function of u through a low pass filtering operation. And as you can see on the spectrum, it's basically the part that contains most of the energy. And the way that this velocity is obtained is by using a traditional LES framework, where one solves the filtered Navier-Stokes equation, where the only thing to point out here is that because of the filtering of the nonlinear term, there is a closure problem that arises in the form of a Subgrid-Scale stress tensor. And this is what I will refer to as a traditional LES closure problem, how to close the Subgrid-Scale stress tensor. But this is not the closure problem I am interested in this talk. Instead, I'm interested in the closure problems that arise in the dispersed phase because of using LES. And this problem is well shown in this equation, where now, in order to transport the particles, while we need the full scale velocity u, we now don't have access to it. We only have access to a large scale velocity. So the closure problem in my entire talk is going to be, how do we model the effect of the small scale velocity u prime on the transport of the particles? In particular, if you look at example of DNS and LES flow field on the right, you can have an intuitive feeling for the fact that the transport of particles can be mispredicted on the right. So the objective is how to design simple models for u prime that can allow in affordable LES computation of particle-laden turbulence to capture the complicated phenomenon that preferential concentration is. And to further motivate why we need such a modeling effort, let me show you what happens if you neglect this problem, meaning that you transport particle either through a full-scale field that you have in DNS, through costly numerical integrations of the Navier-Stokes, or only through the u-bar field that you have in LES without neglecting the small scales. And what you can see right away is that you have a misprediction of preferential concentration, either in the form of underprediction of clustering for low Stokes number, or overprediction of clustering for large Stokes number. And what this points out already is that one of the challenging aspects of this modeling work is that the model that one comes up with for u prime is a model that needs to be able to capture this non-monotonic trend of the impact of the small scales. And it's worth pointing out that the traditional stochastic models that are employed to tackle this problem are not able to actually cluster the particles, and whenever they are added to the simulation, they tend to over-disperse the particles. The second challenge in this work is that there are some regimes in which the characteristic scales of accumulation of the particles, so for example, you can see small scale filament here, typically lie below an LES grid resolution, rendering the capturing of those scales even more challenging when the LES length scale itself is much larger than those cluster length scale. So to tackle this problem, let me first talk about a model I developed, which maybe follow most naturally from modeling the turbulent velocity fluctuation on the LES grid itself. So most of the models that are employed traditionally to model the fluctuating velocity u prime in the Stokes-Drag equation are stochastic or approximate deconvolution models. I already mentioned the main limitation associated with stochastic models. Let me add that both stochastic and approximate deconvolution models that are in the literature suffer from an additional problem, which is that they possess a lot of tunable parameters. So those are parameters that, as a user, you have to tune and decide the value based on this particular flow and application that you are looking at. So in order to circumvent some of those limitations, I started early on by designing a new model for fluctuating velocity on the LES grid by using a different approach. And it is best explained by looking at the relationship between the LES velocity u bar and the full-scale velocity u. So that's a filtering operation. And in most cases, this operation is not invertible. You cannot obtain u bar from u. However, if you make a particular assumption about the choice of the filtering kernel G that relate both velocities, in particular choosing elliptic differential filters that have a filter width related to a model parameter B, then you have an exact relationship that relates the full-scale velocity u and the LES velocity u bar. Meaning that in the continuous sense, at least, you have an exact possible reconstruction of the fluctuating velocity u prime. So the only thing, and this form is worth mentioning, is a simple form that can be used in many complex geometry and complex solvers because it only relies on gradient operators. And the next step with this model is to determine the model parameter B in a way, again, that is dynamic so that the user doesn't have to tune it for a particular application. So next, let's look how I compute the parameter B by taking a step back and reminding that in a point particle LES simulation, now we have two Subgrid-Scale models in the code. The traditional Subgrid-Scale model for the Subgrid-Scale stress and a Subgrid-Scale model for u prime. And it's worth noting that we cannot use for this endeavor the traditional Subgrid-Scale model because they don't provide a u prime. They only provide a Subgrid-Scale stress. So now in the simulation, you have, through the Subgrid-Scale model that you use for the Subgrid-Scale stress, so in my cases, I've been using the dynamics-Magorinsky model, you have an estimate at every time step and every grid point of what is the Subgrid-Scale kinetic energy in your flow. So this is a model quantity, which is an assumption about the Subgrid kinetic energy in your flow. Now, if you do the math with the model on the right, you can also derive an algebraic relationship between what will be that assumed Subgrid-Scale kinetic energy for a particular choice of B. So a natural choice of dynamic procedure is to actually choose B so that these two match. So you can think of it as a consistency constraint dynamic procedure about the subgrid energetics. And if you do the math of what this procedure yields in terms of a final equation for B, it's a simple algebraic equation as a function of the flow parameter that in a code can be solved in a couple of lines and give you a value of B that you can use in the expression for u prime. So that's a simple model, and let's see how it performs first in an isotropic turbulent flow. So the case I'm going to show is one example of a broader campaign over Reynolds number and grid resolution. So I'm going to compare results obtained from transporting particles on a DNS with 256 cube control volumes versus an LES with 32 cube control volumes. And in order to assess the preferential concentration of the particles, I'm going to be plotting the radial distribution function as a function of radial distance. So what this represents is more or less the likelihood to find a given pair of particles separated by a certain separation distance. So the idea is that if your particles were homogeneously distributed, the RDF will be 1 at all radial distances. And when the RDF deviates from 1, it means that you have an increased preferential concentration. So what you see in this plot, by first comparing DNS with LES with WOW model, the both black curves, is that you have under-prediction of preferential concentration for low Stokes, over-prediction for large Stokes, and that in both cases, the model is able to improve the prediction of preferential concentration in the right direction. So this is a quality of the model which is nice, which is that it captures a non-monotonic trend of RDF with Stokes number, unlike traditional stochastic models. However, it's worth noting that the prediction of clustering is still insufficient, in that the blue line lies in between the two black lines. So to further assess where the deficiency comes from, let's look at some instantaneous spatial distribution of particles for two particular Stokes number. For example, at a large Stokes number, where you can see that the LES overpredicts the preferential concentration, and you can see that the result is improved in that you disperse a little bit this accumulation of particles, but not all the way to the level of DNS. And on the left, LES underpredicts the preferential concentration. And when you add the model, what you can see is that the filaments of particles, which on the top figure, become slightly thinner on the bottom figure, but the overall scales around which those filaments organize are not changed by much. Right? And this points out to the fundamental limitation of this first proposed Subgrid-Scale model, which is actually a fundamental limitation of a broader class of model which only models the fluctuating velocity on a coarse LES grid. And so instead, in moving towards a second model, I propose to design a model that recover a fuller scale velocity on a finer grid. So let's say on a red grid here. And so this brings us to the second part of this talk, where now we are tackling the much more challenging problem, where instead of modeling fluctuation on a coarse grid, we are trying to model unknown information on a finer grid. So we want to regenerate small-scale turbulence. And the idea is that we want to regenerate it on a fine grid at a cost which is less than the cost of solving Navier-Stokes on this fine grid. So this is a more complicated problem, and there are less models of this form in the literature. And here I'm just citing the ones that have been assessed in the context of particle-laden turbulence, and reminding below what are some of the issues associated with them. And the main ones is that in addition to the tuning of model parameters, which is also required for most of those, many of them rely on the use of Fourier spectral implementation, which is not practical for real flows that have inhomogeneous directions. Many of them are purely kinematic and have no information about the time dynamics. And finally, some of these models come from the three-dimensional extension of a 1D model, and therefore do not account for the correlation between velocity components, meaning that each component of the velocity is modeled independently. So the model I proposed in that category is a two-step model, where first we model the smallest resolved scale on the LES grid, shown in blue on this spectral representation, just for intuition. And a second step where we enrich the flow with true Subgrid-Scales. And in order to achieve this, we start by applying the previous model that I described, the differential filter model, which goal is actually to add fluctuations on the LES grid. But we had a second step, which I call enrichment here, and which I designed in a way that it provides a velocity field on a grid which is twice finer in each direction. And if you want to go finer than this, you can apply this model recursively. So now let me explain what are the key concepts behind this model by showing how the Subgrid-Scale velocity, which is a component of the full-scale velocity, which is going to contain the actual small scales, is written. So I wrote it as a product of a term that relates to the kinetic energy K and a unitary vector which models at every grid point the structure of the small scales, in that it models the relative orientation of the velocity vector. So to model this structure vector here, I took advantage of the known physical principle through which small scales are generated in an actual turbulent flow, which is through nonlinear interaction of large scales. Now, in our simulation here, since we are doing an LES we do have access to a large-scale velocity. And since in the enrichment step, the first preliminary step consists in going to a finer grid, one can readily compute the nonlinear product of the approximately deconvolved and interpolated velocity on the fine grid with itself, and now have support for the small scales that are generated by this term, with the hope of extracting the dynamical information from the large scale on the fine grid and creating small scales. And we remove from this nonlinear term n the large scale component in an attempt to not affect the large scale which we have already resolved. Now, to model the kinetic energy of the small scales, it is instructive to use a spectral representation, but it's worth mentioning here that this is just for intuitive explanation, but that the entire model is formulated in physical space. There is no Fourier transform at the core of this model. So the idea here is to determine dynamically what is the kinetic energy of the small scale k, so between grid size delta, say, and 2 delta, and to make the assumption that this kinetic energy is proportional to the kinetic energy of the smallest resolved scale, k2, 4 here, between 2 delta and 4 delta. And this assumption is an assumption that can be explained in different ways, one way of which is to say that if you were to have a local self-similarity in your flow, then you will have a parallel spectrum, and you will have a proportionality between these two kinetic energies that does not depend on where you are in your spectrum. So we take advantage of this fact to model this kinetic energy, and the main thing to point out here is that the proportionality constant C is not tuned, but instead is dynamically computed by looking at what is the ratio of kinetic energy between even larger scales. So if you want, in both of these steps, we are trying to use as much information as possible from the large-scale field which we have well resolved. So those are the two key concepts of this model, and now we can revisit the prediction of preferential concentration. But first, let's look at how the flow looks like when this model is applied by looking at a quantity which is very relevant to preferential concentration, the vorticity. Because there is a phenomenological understanding that particles are spun out of vortices and accumulate in high straining regions, and which is one of the mechanisms by which they preferentially accumulate. So that's why we look at vorticity and we compare DNS with LES, and we can see, as I mentioned earlier, that vortical structures are larger and less intense. We can see that the previous model, the DF model, does not lead to generation of small scales, but only to slight intensification of the structures. However, but the SDF model is added in this case 3 times to go all the way to the DNS resolution. We have generation of small scale structures whose intensity, as shown on the color bar, resembles the intensity found in the DNS. And this can be quantified by looking also at the PDF of the vorticity and see that with the SDF model, one can recover the tail associated with the vorticity, which is a very important quantity for clustering. So now when you transport particles through this flow and you assess the preferential concentration to the radial distribution function again, what you can see is that the model further improves the preferential concentration in a wide range of Stokes number and brings these curves close to the DNS levels. And this is something that you can see also on the spatial distribution, where now the improvement compared to the DF is significant, both at large Stokes and also at small Stokes. And a compact representation of this phenomenon can be obtained by estimating from these Lagrangian positions of particles a particle number density, and then computing the spectrum of this field to obtain a scale decomposition of the variance and be able to assess what are the scales that contribute the most to the variance in this flow. And when you do this for a low Stokes number, you can see that there is a significant clustering at high wave numbers because these particles primarily interact with those small scales. And the model that basically regenerate all the flow length scales shown in this green area is able to cluster the particles at these very small scales. But also in the opposite regime, where actually the particles accumulate at large scale, still in this regime, the small scale play an important role, and the model is able to have a broadband impact on the prediction of preferential concentration. So this model, by the way, the SDF model, which is a dynamic model that generates small-scale turbulence, is not restricted to particle-laden turbulence. And actually, I want to show here an example of a collaboration with Professor Ehrman from Arizona State, who during the last summer program, in a short time, implemented this model and tested it to predict the corrugation dynamics of an interface in a multi-phase flow, and was able to show that he also obtained good agreement for the volume of fluid scalar field in these three-dimensional computations. And there are other applications where such a model can also be employed. So in the next section, going maybe back to the original application I mentioned, I want to talk about the application of those models to wall-bounded flows, and in particular, what are the challenges in predicting preferential concentration in the presence of a wall. So in a wall-bounded flow, so here I'm showing an example of a turbulent channel flow as friction Reynolds number 600. The traditional direct numerical simulation approach is also prohibitively expensive, and you can see here the number of points required to capture this flow is very large. So instead, the approach that I want to take in this section is the approach of wall-modeled LES, where instead of a stretch mesh that resolves the near wall eddies, we have a uniform mesh throughout the channel, and now not only we do not resolve the flow length scale in the core, but we are also not resolving the primary structures of the flow near the wall. So here I want to emphasize the fact that we have a very coarse resolution with only 20 points across the channel, which render a first cell which is 2 orders of magnitude larger than in the DNS. And in the core, it is about 10 times larger than in the DNS. And the bold question here that I ask is it possible at this affordable cost to predict the spatial distribution of particles? And the reason that it may seem to be a reasonable question is that there are a number of single-phase flow wall models that have been developed over the past years that actually, even at that coarse resolution, enable to obtain reasonable flow statistics. So here I'm showing a single-phase flow statistics, for example, the mean flow velocity for the streamwise component, and you have a reasonable agreement for the velocity. But there is no work on the prediction of particle-laden turbulence in wall model channel flow. So this is the first attempt at seeing what does it take to predict this phenomena at such a cheap cost. And it's worth pointing out that the two additional physical components that were not present in the previous section now are, on one hand, the near-wall particle dynamics, so interaction of particles near the wall, and in particular with the turbulent streaks near the wall. And the second one is the presence of inhomogeneities in the flow. So for this problem, there is a lower order statistics than the RDF, which I couldn't show before in isotropic turbulence because it didn't make sense there, which is to know, as a function of the wall distance, where are particles. And so this can be assessed by looking at the mean concentration profile as a function of y. And here, the concentration profile is sampled on the wall model LES mesh in order to answer a simple question, which is, at the scale at which I'm solving for the flow, am I able to resolve the characteristics of the particles? And what you can see is that for all wall model LES attempts, whether they include or not the Subgrid-Scale models which I described earlier, you are not able to obtain a reasonable prediction of where the particles are in the channel. In fact, in the first cell near the wall, you are predicting twice as many particles as there should be, which in turn, for this low Stokes, results in 10 times less particles throughout the rest of the channel, or half time less particles for the high Stokes number. So what this indicates is that the fact that there is really no effect of these models is that there is something else that is needed to predict the concentration profile in this particular flow. And to take a closer look, you can look at the concentration profile, which I shown before, but sample on a finer mesh to have a more faithful representation of how it evolved in space. So this is what this figure showed, concentration profile on a finer mesh and in log scale. And the dashed line here represents the location of the first control volume. So what this cell shows is that actually most of the gradients of the concentration profile in a typical wall model LES calculation are contained within the first cell. So now if you think back of the Subgrid-Scale models, which I presented earlier, that really play, for example, for the DF model with the LES velocity at the first grid cell, they are not going to really impact the behavior of the particles in between that much to obtain this profile. So what this calls for is a particle wall model, a particular treatment of particle in the first cell, which is different than a Subgrid-Scale model as I described earlier. And so a proposed wall modeling strategy, which I want to describe here as a first attempt, a simple attempt to see if we can correct for this concentration, is to use improved interpolation kernels in the first layer, meaning that if a particle is in the first cell of the wall model calculation, instead of using a traditional interpolation scheme to compute the velocity that it sees, so interpolation between the first LES grid point and the wall, instead, so these interpolation kernels, by the way, I represent here for the streamwise as f, or for the wall normal velocity as g. Instead, can we use a more faithful representation of the flow velocity within that first cell? So it turns out that for the streamwise velocity, there is a theoretical prediction from the law of the wall in wall channel flow that one can use, which is a better prediction of the streamwise velocity of the flow in the first cell. So it can be used to estimate the flow velocity at the particle location. Now when it comes to the flow wall normal velocity at the location of the particle, this is a much more complicated challenge because there is no such theory, there is no law of the wall for the wall normal velocity. So as an attempt to see what it takes, in this proposed modeling strategy, the functional that relates the velocity in a wall model LES calculation at the first point to the one used for the particles is numerically estimated from DNS data. And what this yields, before looking at the concentration profile, typically is that now if you look at the variance of the particle velocity as a function of y, the magenta curve that uses this particle wall model, you can see that the magenta curve now resembles the profile obtained from DNS. And the reason that I'm showing here this wall normal particle velocity is because it can be shown from theoretical analysis to be a very important factor to predict the turbophoretic effect by which particles accumulate near the wall. So now if we look at the effect of this simple particle model on the concentration profile, one can see that for large Stokes number particle, there is a significant improvement of the concentration, in that near the wall you can obtain values which are very close to the DNS profile, and same in the core. However, for low Stokes number, there is no improvement. And actually, in this case, the result gets even slightly worse. And so this owes to the fact that low Stokes number particles require way more than just the flow statistics in the first cell, but they actually require the structure of the flow in the first cell. So what this says is that although this wall modeling strategy in particle-laden turbulence is a sufficient exercise for large Stokes number, to be able to predict the concentration profile at large Stokes, more work needs to be done, and in particular the development of more physics-based model that captures the structures in the first cell, as opposed to simply the statistics of the flow there. So this is the story for the concentration profile that tells us in a wall model calculation where are the particles as a function of distance from the wall. Now we can look at the higher order statistics which we were looking at before, which is now at a given y location, for particles that are there, how are they organized? Are they clustered or are they not clustered? And for this we can look at the radial distribution function again as a function of wall normal distance. And to be able to affect and tackle this problem, now we are using the Subgrid-Scale models which I presented in the two previous parts. And here it is worth mentioning that in order to apply these models to these wall cases, I didn't have to do any changes to the model formulation, in that from the start, they were written in a way that they can be easily implemented in this different flow and different solver. So what you can see here is that for large Stokes number, so viscous Stokes number of order 100, the models are able to disperse the particles throughout the channel closer to the DNS. But at a lower Stokes number, only closer to the core, the model clusters the particles. But the Subgrid-Scale models are not able to dictate the behavior of the particles near the wall, consistently with what we just showed before, which is that for this low Stokes number and close to the wall, we need better models. And first, we need a particle wall model to predict where the particles are. So now here, it is worth mentioning that the red curve, which is obtained from applying the spectrally enriched differential filter, contrary to the results shown for isotropic turbulence, does not correspond to a flow field that is regenerated all the way to the DNS level. It simply corresponds, for illustration, to one reconstruction level. And instead of further investigating what would be the effect of regenerating more levels with a differential filter, with a spectrally enriched differential filter on this plot, I want to move to the last part and try to answer a different question, which is relevant to this one though, which is that in an actual flow, rather than using this spectrally enriched differential filter uniformly in space, would it be possible to use it only in particular regions of the flow and have a sensor that prescribes how many levels of reconstructions might be needed depending on when you are in the flow? And so for this, in this first part, I'm going to describe such a sensor that is based on wavelet analysis of particle-laden turbulence. And before describing the methodology, let me describe why in the first place I performed an analysis of particle-laden turbulence by showing here a picture of preferential concentration, where on the left you have 3 Stokes number and a random distribution for contrast. And going from left to right, we zoom into the red boxes. And the main idea here is that you can see that in addition to being characterized by intense spatial localization of particles, preferential concentration is also a very multi-scale phenomenon. And at some Stokes, it pervades throughout the range of scales. But at large Stokes, it does not and stop at some intermediate scale. So the fact that preferential concentration is both a well localized, say, in physical space, but also in spectral spaces, most of the analysis so far of preferential concentration had been done in physical space or in spectral space, meaning that whatever analysis was conducted was very well localized at every grid point, but no information about the wave number associated with the results. Or on the other hand, was very well localized in spectral space with no information about the spatial localization of the information. So instead, wavelet is an example of basis function that allows you to get information localized both in spectral space and in physical space. So now let me describe to you the method that is based on wavelets, and that is based on a first step which consists in estimating the particle number density from the Lagrangian spatial distributions, and then at computing the wavelet transform of this field. So when you compute the wavelet transform of the particle number density, you have wavelet coefficient, which I show here as n tilde. And the main idea of this method is to separate the wavelet coefficients of the particle number density into large wavelet coefficients that correspond to energetic structures in the particle number density field from low wavelet coefficients. Now, what is large, what is low? So it turns out that there is a result from statistical theory, from actually from Stanford by David Donohoe, that prescribes the thresholds as a function of the field itself. So what you can do is separate the wavelet coefficients into 2 sets, and from each of these sets, reconstruct 2 different particle number density fields. And when you do this, what you obtain is a decomposition of your full scale, the full representation of the particle number density into the sum of what I call a coherent component, shown in red here, and an incoherent component, shown in blue here. And it is striking from this decomposition that the incoherent component is pretty structureless, while the coherent component in red is the one that actually contain the information about the clusters. What is even more striking is that the red component is obtained in this case by retaining only 1.6% of the total number of wavelet coefficients of the green field. So it's a very high compression rate, and furthermore, this compression rate was obtained at Stokes 1, which is the most difficult case because this is the one where you have the most small-scale clusters, and it drops on both sides of these plots. So the main conclusion from this analysis based on wavelet filtering is that the wavelet coefficients act as efficient sensors to detect the spatially localized fluctuation of the particle number density and at different scales. And since you are able to, by retaining only a few of those wavelet coefficients, detect the structures efficiently, you can build a grid refinement algorithm based on this. By identifying a given wavelet coefficient with a given control volume, and thanks to the localization of the wavelet coefficient both in physical space and spectral space, you both have the location of the control volume and the scale associated with it. And so now I can show an example of the type of grids that this dynamic sensor will produce by using here data at Stokes 1, where you can see that the grid dynamically has adapted around the particle sheets in this case. And at larger Stokes, where there is no small-scale cluster in this region of the flow, the grid hasn't produced small control volumes. So in these two cases, the reduction of number of control volumes is by 1 order of magnitude on the left and 2 orders of magnitude on the right. And so what this calls is basically for a combination of this strategy with the previous Subgrid-Scale modeling strategy which I proposed for a non-uniform application of basically the spectral enrichment in space. So in summary, I like to show this picture to kind of give an overview of what are the different modeling strategies that I have talked about, and in particular remind that actually they all build on each other and they can be combined. So on the left was a non-spectrally enriched Subgrid-Scale model, which is a differential filter model. In the middle is a spectrally enriched differential filter model built on a finer grid than the LES grid. And on the right is the definition of a wavelet-based dynamic sensor that give you an estimate of where in your flow you should actually potentially apply these models which I talked about. And so if you want more details about each of these parts which I tackle in this flow, you can find those in these articles. And also some other published contributions which I haven't mentioned in this talk are related to using control-based numerical scheme for force turbulence simulations, or also a broader campaign of wavelet analysis for preferential concentration, energy transfer in turbulent premix combustion, and rendering of the turbulent energy cascade. And finally, a work on the use of linear algebra and complex analysis for improved and more robust explicit time advancement schemes. And so with this, I want to end my talk and do some acknowledgements by first thanking the sponsor of this research from the Department of Energy through the PSAP program. I also want to thank the oral committee for my defense. So Professor Wallet, thank you for chairing the defense. Special thanks to my advisor as well, Parviz Moin, for the mentoring over the years, first trusting me to take me in your research group, and then having supported me throughout the years in high and in low moments and giving very good research feedback. I also want to thank Javier for also the invaluable help from day one to today into really gaining scientific insights about all of this problem and being very available whenever I needed it for anything related to my research. I really appreciate it. I want to thank also Ali Mani. Thank you very much for some of the research collaborations we have had, but also a lot of the classes I've taken with you. I've learned a lot. And I cannot say how thankful I am to everyone, but I'm just mentioning it and you know what I mean. Yeah, and I want to thank the last member of my old committee, Sanjiva Lele. I've also learned a tremendous amount from your class, which I've always considered as documentaries about the fundamentals of turbulence. And I've really enjoyed learning from you both in meetings and in class. And this is the occasion for me to also thank more faculty at Stanford from whom I've taken classes, but also in particular the PSAP program and its director, Gianluca Iacarino. I'm very grateful for having been part of this program. It has been an amazing experience for me to actually, during my PhD, be part of such a large research team and hear from different faculty, different teams, different PhD students and postdocs, and I can't thank everyone enough for that. Also, I want to thank some of the external collaborators I have made throughout these 5 years. Daniel at Los Alamos, Kai in Marseille in France, and Marcus Herman more recently in Arizona State. I want to thank everyone that has crossed my path, whether CTR postdoc, student in Moin's research group, or employee, or students in other labs in Building 500, and also all of my friends that I've made at Stanford. And yeah, I'm not very good at acknowledging, but I'm very grateful to everybody, and I will keep it to that. And I will just end with thanking my family, my parents and sisters, and grandparents, and also I want to thank my fiancée, Sadaf, who has been an unconditional support during the 5 years, and her entire family, in particular parents, sister, and sister's husband, and we are all represented in this picture. Or you can see I kind of already celebrated this day not so long ago, and in continuing my journey in life, I'm glad to announce that my future father-in-law is named Parviz, like my PhD advisor. So yeah. So I won't forget you. Anyway, thank you everybody, and thank you.